Our speaker today is Tang, and she is going to talk to us about the work he's been doing together with coworkers on interactive chemistry for E3SM. So thank you very much, and take it away, Chi.
Yeah, thanks for the invitation. This is a working project, so I will focus on the new capabilities and the initial results from the interactive chemistry development for E3SM. This is a collaborated work between the Livermore lab and the UC Irvine. I would like to first Minxue and Hailun's aerosol group for creating the CMIP6 emissions and the computational resource at compy and NERSC. So before I go into the atmospheric chemistry, it's helpful to look at the so the blue boxes showing are the existing physics packages, including deep and shallow convection, turbulence macrophysics, microphysics, radiation, atmospheric physics, chemistry, and aerosols. So in the dash box is the corresponding new development the E3SM V3 development is working on. And our chemistry and radiation work highlighted in the orange box includes the integrating UCI chemistry, fast-J photolysis, and the solar-J radiation module in E3SM V3. And our work is closely related to BGC and aerosol development. I'm going to talk more later. So for the atmospheric chemistry and the radiation task, we aim to add the ability to project future greenhouse gas based on emission scenarios in a changing climate. So we will support biogeochemistry and aerosol chemistry, including short-lived chemistry forces. So what we start from is the E3SM V1 chemistry. We call it ozone V1. In the stratosphere, we have linearized interactive ozone, Linoz version 2, and the tropospheric chemistry is prescribed oxidants for aerosols. A major weakness for this ozone V1 is that it misses the tropopause variability, especially at the jet regions. To fix that, in E3SM V2 chemistry, ozone V2, we changed the tropospheric ozone to a passive tracer with lower boundary sink, which maintains the sharp cross-tropopause ozone gradient, and we are able to diagnose the stratosphere-troposphere exchange flux of ozone, a major tropospheric ozone budget. So starting from that, we already have some publications in E3SM recently. In this one, we evaluated the stratospheric ozone in ozone V2. On the left side shows the zonal mean stratospheric column ozone annual cycles from the satellite observation, UCI chemistry transport model, CTM, and ozone V1 and ozone V2. Clearly, we see overestimation of ozone V1 in the middle to high latitudes, and it has been corrected with the ozone V2 package. On the right-hand side shows the daily southern hemisphere minimum total column ozone, and the ozone V2 matches the observations reasonably well. So in conclusion of this paper, we found that the stratospheric column ozone is reasonably captured by Linoz V2, including the Antarctic ozone hole. So on the radiation development side, we realized in this paper documents that the flat atmosphere assumption, which normally in the climate model is commonly used, and it looks like this, whereas in reality it's round Earth, so atmosphere is curved. So in the model, when we apply the flat atmosphere assumption, we need a correction for the radiation errors. So in this paper, we found that the flat atmosphere approximation leads to regional errors in solar heating comparable to the climate forcing by greenhouse gases and aerosols. So this round Earth fix is included in the FastJ code in E3SM right now, but it's not enabled for radiation transfer calculation. So we also assessed the errors and uncertainties in the solar heating code, and with recommendations. We identified, we went through the exhausted list of possible error sources and identified those larger ones, and then the ones need to be fixed. So our current status is that we spend significant effort in the code development, and not long ago, all the major pieces are finally on the E3SM GitHub branches, including the chemistry and the radiation. For the interactive chemistry, we have updated Linoz to version 3 in the stratosphere, and enabled the UCI chemistry in the troposphere, and is ready to be linked with the BGC experiment, such as the methane experiment and other scientific applications. The FastJ photolysis rates replaces the lookup table and is coupled with the superfast chemistry and can be easily further coupled with the ChemUCI chemistry. So with those new code, we can now finally start to work on address science questions. In the following few slides, I'm giving you a few detailed information about the E3SM V3 tracers and the reactions. So a major point for the E3SM V3 chemistry is that it's fast, which is critical for climate models to have interactive chemistry. And the major reason why in previous climate models is normally not included. So our initial test shows that the interactive chemistry can achieve about 12 simulation years per day on only 30 nodes on compy. This is only about 8% of the additional computational cost added to the 1 degree standard E3SM model. So for the stratosphere, we advanced we carried 4 tracers: ozone, methane, N₂O, and NOAA. And on the right table, I shows the tracers for the tropospheric chemistry. For methane here, I put a star because it can be either prescribed or interactively. For the BGC experiment, we needed to be an interactive tracer. Some of the tracers, like OH, we don't necessarily need to adapt it. It's just a software issue here. So for now, we adapt it, but that can be further improved along with some other aspect of the chemistry implementation. So this throughput, I expected that's just the starting point. We can further improve it. And to separate the stratosphere and the troposphere, we introduce the identify tropopause tracer. It's an artificial tracer, E90, with uniform surface emissions and 90 days e-folding decay time everywhere in the atmosphere. For the reactions, you can find on this GitHub link. So with the new code now available on E3SM branches, I'm giving you a few examples what kind of science questions we can work on. So with the ChemUCI in USSM, we can study the interactions between tropospheric pollutants and the greenhouse gases. The blue box, this figure shows the key species of the tropospheric chemistry. The blue box is the radicals driving the tropospheric chemistry on a timescale of a few seconds. The green boxes are the direct greenhouse gases, whereas the red box are the indirect greenhouse gases. Those pollutants can affect other greenhouse gases through tropospheric chemistry. So with ChemUCI and the Linoz V3, we can look at the interactions between stratospheric and the tropospheric chemistry with aerosols, including sulfate, secondary organic aerosol, SOA, and nitrate. And we can also look at the BGC interactions with chemistry, including methane emissions, volatile organic carbon emissions, oxidant damage to vegetation, nitrate fertilization, and NOAA emissions. So the major chemical pathways are already there. Some may, if we target on some specific questions, may need to enable or add in the existing ChemUCI mechanism. But the major parts are already on E3SM. So we aim to design ChemUCI and Linoz version 3 for the major CMIPs. So what are mainly evaluated for existing CMIP6 emissions? We cannot do that with the old E3SM versions, but we'll be able to enable them for the E3SM version 3. So showing here are the stratospheric ozone and water vapor, which are both important for climate change and projections in the future. So we have observations, more reliable observations since 1980s. So to evaluate the stratospheric ozone columns, and also will be it's also important for the climate models to match out the historic ozone depletion in the stratosphere and the recovery later on with various scenarios in the projection. Also for the surface ozone, in the tropospheric ozone, we have the surface ozone trends. We know we have observations can be evaluated against, and also the geographic patterns of tropospheric column ozone, and then the burden in the historical and future time periods. So we can also look at the methane lifetime, which some of the models shows very unrealistic patterns there. And we have some observational evidence of the tropospheric hydroxyl radicals, OH. So we can use that to infer the, to evaluate the methane simulations. So that's important for the radiative effects of the simulated climate history in the history and also into the future. So this one is interesting and more related to the BGC is that we can actually find observational evidence in the vegetation feedback on the tropospheric air pollutant. So when there's a drought, then the vegetation will be suppressed and reduces the dry deposition of ozone to the surface, and then will make the air pollution worse. So with the Linoz V2 stratospheric column ozone, we found that it matches not only the observations, but also the UCI and the Goddard GMI CTMs, as shown on this Taylor diagram. So we are happy about that. But when we push the limit to look at the interannual residuals, none of the models, including the chemistry transport model, cannot fail to capture the signal in the observations. So we developed a new diagnostic to look at the QBO signal as a composite. So this diagnostic will work better to evaluate the chemistry climate models, and we are going to apply that to E3SM V3. So for the FastJ implementation, on the left, I show the lat long maps. So the improvement from FastJ over the lookup table is that it can it reduces the bias in the clouds and the aerosol interactions to the photolysis rate. So we see the enhanced photolysis with the light reflecting of ice in the NO2 photolysis rate, and there are regions covered by clouds. And for the O₀D photolysis is mainly driven by the UV radiation, so it shows so it peaks at where the sunlight is overhead. So with the FastJ photolysis, we'll have consistent treatment for overlapping clouds and aerosols. And also the code, as I mentioned before, already has that rounders fix. For the multi-angle scattering, what important for BGC is that it can provide more realistic diffusive PAR incidence on ocean and the biosphere. So that's some potential directions we can work on in collaboration with the BGC group. So for Linoz V3, I know some of you are not so familiar with it, so I'm going to provide some details. So in Linoz version 2, we only have a single trace ozone in the stratosphere, but for version 3, we have N₂O, NOAA, and methane, and also water vapor in the stratosphere. So the four prognostic equations are for those four tracers, N₂O, NOAA, ozone, and methane. So the equations are solved in the same way as Linoz version 2 as a first order approximation of the Taylor expansion around the monthly mean, zonal mean, chemical climatologies of the in situ concentration, overhead ozone column, and the temperature, local temperature. So the derivative terms are derived by the UCI box model. Then the stratospheric water vapor is diagnosed from the methane change with assuming a lower boundary at the tropopause value and the conservation equation of this. And the stratospheric chlorine and bromine levels are set to the climatology. So the Linoz tables are calculated for the historical or projected levels of those halocarbons. So if we change the future projection scenarios, then the tables will need to be recalculated. This gives a example of the applying Linoz V3 to study the coupling between the stratosphere and the troposphere chemistry. So it's found that when we perturb the N₂O emission by 10 teragrams, then this will induce a perturbation on the about 108-year global eigenvalues, and the methane, ozone, CO, they will decay according to that eigenmode. So provide a useful application to study what those tracers will be with certain perturbations. And this figure shows the eigenmode distribution. So to evaluate the initial implementation of Linoz v3 in E3SM, we plotted out the pressure by latitude plots for those 4 species. They look reasonable and matches the observations. Methane and N₂O has surface emissions, so the maximum is at the bottom part, whereas NOAA and ozone has stratospheric sources. So it's identified on those 2 figures. So this one is already on the E3SM GitHub branch. But in the simulations, the results I'm going to show in this talk, we still use Linoz v2 because our focus is mainly on the ChemUCI for that simulation. So for the tropopause defined by E90, it's clearly separate the stratosphere and the troposphere in 3D. The 2 figures shows the tropopause identified by E90, and we see the folding in this region, and the E90 method has advantage over previous tropopause definitions to identify those folding events, which are important for the interactive chemistry. So the with the equivalent emissions of the E90, the E3SM tropopause threshold actually is smaller than the UCI CTM. So this actually provides a new diagnostic of the efficiency of tropospheric mixing. And the smaller tropopause threshold suggests a slower mixing of E3SM than the ECMWF winds, which is used to drive the UCI CTM. Also, E3SM tropopause is currently defined as a 2D field. We need to implement the 3D tropopause in E3SM for chemistry. Tropospheric chemistry, especially the trends and variability, are mainly driven by the surface emissions. So here I plotted out the NO and the biogenic isoprene emissions to give you a flavor what the CMIP6 emissions looks like. We have hotspot over the land for NO, over the polluted regions, and the biogenic isoprenes are mainly in where are those forests are, and mainly in the tropics. So we ran the ChemUCI with Linoz v2 for 15 years from 1995 to 2000 to 2009. Then we analyzed the last 10 years of the results. Showing here is the tropospheric column ozone versus the satellite observations derived from OMI and MLS data. So the annual mean of the model, annual mean DJF and the JJA means of those 10 years, comparing the model on the left, observations in the middle, and the difference on the right, shows a reasonable comparison between the model and the observations. The if we put we can see that the model mainly overestimate over tropical lands and underestimate over the oceans. But we didn't. I got those results not long ago, so we need to analyze more to understand what's driving the model of differences. But as initial results, they look pretty good. And if we put them those patterns on the Taylor diagram, the normalized root mean square differences are very close to 1, and the correlations are also well simulated, except for the DJF, the winter months, because of this low bias. So the model is reasonably working for the tropospheric chemistry, and then we also look at the CO at surface compared to NOAA observations. On the left shows the NOAA sites. It has very good global coverage. The red ones are the one with longer time period, and which shows on the right-hand side. The red dots means when the monthly mean data is available. So we have a good number of NOAA sites as long time observations. So we pick those with data over 20 years and not close to mountains or polluted regions for our evaluation. So at this site, the barrier site at Northern Hemisphere high latitudes, on the top, we see the time series NOAA data in red and E3SM in blue. So we have a low bias there, and the trend is perfectly matched because it's driven mainly by the surface emissions, not the chemistry. And the annual cycle, so this we filtered the signals above annual cycle. So what left is the annual cycle and the subharmonics. On the annual cycle, the magnitude and the phase also matched well. We missed the minimum there. So seems suggesting some months there is more problematic than other months. So at this site in the tropics, we also have low bias, but the trend is so the decreasing trend is greater than the observation, but the annual cycle is almost perfectly matched. And if we look at a site this site is over the Central Pacific and affected by the ITCZ, so it shows the high mean bias because it's affected by the ITCZ air outflow from that region, and also misses the maximum and the minimum of the annual cycle. So it can be used as a additional diagnostics to identify those model dynamic issues, or maybe related as well, or also to the physics. So we can also reasonably match the NOAA site at South Pole. So this is a Antarctic site. Has some overestimation, but the annual cycle is reasonably captured. So overall, for the surface CO simulation, we match the global sites with a relatively good comparison with the NOAA observations. So then we move to the methane loss rate. Showing here is the loss rate for year 2000, plotted by annual January and July means for the methane loss. So we see where the methane is mainly lost in the model in the northern hemisphere tropics, and can see the seasonal shift of the loss region, and in the summer months, some of those middle to high latitude also can show some of the methane loss there. So it implies because the methane is prescribed in this round, the changes showing here in the methane loss rate implies the OH changes. Since we didn't get the results, so we only got the results recently. So we have some ongoing work to do with more metrics. One of them, as I show here, is the air quality. We can look at the surface ozone and the PM aerosols compared to observations. So those observational network, mainly in the US and in the Europe. So we can also compare with the ATOM recent measurements. So this figure shows the aircraft sampling tracks of the ATOM measurements. So it goes through where most of the methane loss occurs. And there's a paper under review shows the Atlantic ozone methane loss. So we can also sample the E3SM to see if we can match this observed methane loss. There are also a bunch of other species measured by the aircraft, which can also provide valuable observational data to evaluate our E3SM chemistry. So that's where the flight tracks are. So you see it goes up and down, and the methane loss changes with height and latitudes. So in summary, we implemented ChemUCI and Linoz V3 interactive chemistry on a E3SM V2 beta code, and it's on a remote branch on the GitHub. Initial results show reasonable tropospheric column ozone and the surface CO compared to observations, and it's ready for BGC and aerosol links. So we need to further evaluate the chemistry results against observations, and along with that work, we'll define new chemistry metrics for E3SM diagnostics, and also hopefully we'll get extra human resource to also work on implementing those new chemistry metrics into the routine E3SM diags, so we can evaluate the chemistry performance routinely when we develop E3SM future versions. So we are working on with BGC group defining the interface for interactive methane and ozone simulations. So we have regular meetings, and then we can also start work on the aerosol team link with chemistry and aerosols. So so I'll stop here and take questions.